The critical path method is an algorithm for scheduling a set of project activities. History. The critical path method is a project modeling technique developed in the late 1950s by Morgan R. Walker of DuPont and James E. Kelly, Jr. of Remington Rand. Kelly and Walker related their memories of the development of CPM in 1989. Kelly attributed the term critical path to the developers of the program evaluation and review technique, which was developed at about the same time by Booz Allen Hamilton and the U.S. Navy. The precursors of what came to be known as critical path were developed and put into practice by DuPont between 1940 and 1943 and contributed to the success of the Manhattan Project. CPM is commonly used with all forms of projects, including construction, aerospace and defense, software development, research projects, product development, engineering, and plant maintenance, among others. Any project with interdependent activities can apply this method of mathematical analysis. Although the original CPM program and approach is no longer used, the term is generally applied to any approach used to analyze a project network logic diagram. Basic technique. The essential technique for using CPM is to construct a model of the project that includes the following: a list of all activities required to complete the project, the time that each activity will take to complete, the dependencies between the activities and logical endpoints such as milestones or deliverable items. Using these values, CPM calculates the longest path of planned activities to logical endpoints or to the end of the project, and the earliest and latest that each activity can start and finish without making the project longer. This process determines which activities are critical, and which have total float. In project management, a critical path is the sequence of project network activities which add up to the longest overall duration. This determines the shortest time possible to complete the project. Any delay of an activity on the critical path directly impacts the planned project completion date. A project can have several, parallel, near-critical paths. An additional parallel path through the network with the total durations shorter than the critical path is called a subcritical or non-critical path. CPM analysis tools allow a user to select a logical endpoint in a project and quickly identify its longest series of dependent activities. These tools can display the critical path as a cascading waterfall that flows from the project start to the selected logical endpoint. Although the activity on arrow diagram is still used in a few places, it has generally been superseded by the activity on node diagram, where each activity is shown as a box or node and the arrows represent the logical relationships going from predecessor to successor as shown here in the activity on node diagram. In this diagram, activities A, B, C, D, and E comprise the critical or longest path, while activities F, G, and H are off the critical path with floats of 15 days, 5 days, and 20 days respectively. Whereas activities that are off the critical path have float and are therefore not delaying completion of the project, those on the critical path will usually have critical path drag, that is, they delay project completion. The drag of a critical path activity can be computed using the following formula: if a critical path activity has nothing in parallel, its drag is equal to its duration. Thus A and E have drags of 10 days and 20 days respectively. If a critical path activity has another activity in parallel, its drag is equal to whichever is less, its duration or the total float of the parallel activity with the least total float. Thus, since B and C are both parallel to F and H, B has a duration of 20 and drag of 15, while C has a duration of only 5 days and thus drag of only 5. Activity D, with a duration of 10 days, is parallel to G and H and therefore its drag is equal to 5, the float of G. These results, including the drag computations, allow managers to prioritize activities for the effective management of project completion, and to shorten the planned critical path of a project by pruning critical path activities, by fast-tracking, and/or by crashing the critical path. Crash duration. Crash duration is a term referring to the shortest possible time for which an activity can be scheduled. It is achieved by shifting more resources towards the completion of that activity, resulting in decreased time spent and often a reduced quality of work, as the premium is set on speed. Crash duration is typically modeled as a linear relationship between cost and activity duration, however in many cases a convex function or a step function is more applicable. Expansion. Originally, the critical path method considered only logical dependencies between terminal elements. Since then, it has been expanded to allow for the inclusion of resources related to each activity, through processes called activity-based resource assignments and resource leveling. A resource-leveled schedule may include delays due to resource bottlenecks, and may cause a previously shorter path to become the longest or most resource-critical path. A related concept is called the critical chain, which attempts to protect activity and project durations from unforeseen delays due to resource constraints. Since project schedules change on a regular basis, CPM allows continuous monitoring of the schedule, which allows the project manager to track the critical activities, and alerts the project manager to the possibility that non-critical activities may be delayed beyond their total float, thus creating a new critical path and delaying project completion. In addition, the method can easily incorporate the concepts of stochastic predictions, using the program evaluation and review technique and event chain methodology. Currently, there are several software solutions available in industry that use the CPM method of scheduling. See List of project management software. The method currently used by most project management software is based on a manual calculation approach developed by Fondal of Stanford University. Flexibility. A schedule generated using critical path techniques often is not realized precisely, as estimations are used to calculate times. If one mistake is made, the results of the analysis may change. This could cause an upset in the implementation of a project if the estimates are blindly believed, and if changes are not addressed promptly. However, the structure of critical path analysis is such that the variance from the original schedule caused by any change can be measured, and its impact either ameliorated or adjusted for. Indeed, an important element of project post-mortem analysis is the as-built critical path, which analyzes the specific causes and impacts of changes between the planned schedule and eventual schedule as actually implemented. See also, Gantt chart, list of project management software, list of project management topics, project management, project planning, work breakdown structure, float, references. Further reading, Project Management Institute. A Guide to the Project Management Body of Knowledge. Project Management Institute. ISBN A978-1-935589-67-9. Klastorin, Ted. Project Management, Tools and Trade-offs. Wiley. ISBN A978-0-471-41384-4. Harkins, Gary. Project Management. McGraw-Hill. ISBN A0-07-137,952-5. Harold Kurzer. Project Management, a systems approach to planning, scheduling, and controlling. ISBN A0-471-22577-0. Lewis, James. Fundamentals of Project Management. American Management Association. ISBN A0-8144-7132-3. Milosevic, Dragon Z. Project Management Toolbox, Tools and Techniques for the Practicing Project Manager. Wiley. ISBN A978-0-471-20822-8. O'Brien, James J. Plitnick, Frederick L. CPM in Construction Management, 7th edition. McGraw-Hill. ISBN A978-0-07-163664-3. Wolf, Murray B. CPM Mechanics, The Critical Path Method of Modeling Project Execution Strategy. ICS Publications. ISBN A978-0-9854091-0. Wolf, Murray B. Faster Construction Projects with CPM Scheduling. McGraw-Hill. ISBN A978-0-07-148660-6 Trauner, Manginelli, Low, Negator, Furnice. Construction Delays, Second ed. Understanding Them Clearly, Analyzing Them Correctly. Burlington, Massachusetts, Elsevier. PA 266. ISBN A978-1-85617-677-4. Malakuti, B. Operations and Production Systems with Multiple Objectives. John Wiley & Sons. ISBN A978-1-118-58537-5A.